So, hello everyone. My name is Ahmed Abdellah. I am research associate at University of Calgary. I was formerly working as a research associate at McMaster University under supervision through Higgins. So today I will present our recent paper published in Small Method. It's talking about like the in-situ transmission electron microscope for promote like the workflow, technical advances that are challenging, and the lesson to learn, and how we get the best performance to do in situ liquid and get high resolution imaging. So today for this talk, we talking about the workflow summary for the in situ electrochemical experimental work. So we're talking about two parts. The first part will talking about the technical consideration you have to consider when you plan to do any electrochemical measurement under the in situ liquid cell. So we're talking about the liquid cell configuration, the microchip preparation, and the electrode preparation. And after that, we're talking about what the acquisition consideration need to take care about it, like how you control the liquid thickness, how you do like yields or EDX mapping, and how you can manage the electron dose under the electrochemical condition. So first of all, like here, this is the prototype system. As all you know, like we have here the TM holder, and you have two silicon nitrile window. One of them, they have the 3 electrode printed. You have the working electrode, reference electrode, and counter electrode. And in the back of the holder, it's connected with the potentiostat, and we can control the electrolyte flow inside the holder using the syringe pump. And in the bottom image here, you can see how we assembly this holder. Like we use a gasket, both after that you deposit like the insert the small E-chip, and after that you do the large chip and close the holder. And we do your experimental work. But for the syringe pump, we face like in specific electrochemical measurement, like carbon dioxide reduction. We face like in this specific measurement, the syringe pump doesn't affected working well with our experimental due to like as we use saturated solution for carbon dioxide reduction under this condition. So to get the solution very saturated during the whole session, so we face some limitation using the syringe pump, so that we modify the system quite a bit, like by replacing the syringe pump using the pressurized pump. So where you can use the pressure gas, as you are interested. In our case, we use the carbon dioxide gas as a pressure gas to force the electrolyte flow under the through the holder, so we can keep the solution all the time saturated. So you can see these two examples. In the first one, when we're using the syringe for longer time, so you can see by the time some of the oxygen can sweep in the syringe pump, so that we can see some effect of the electrochemical behavior of the palladium. Compared to when we use on the other side, if you use the pressurized pump, we can get like very sharp peak of the for the palladium reduction peak, and this compared to the ex situ measurement. So we have controlled the electrochemical environment using the pressurized pump. So it depends like what the application you are using. If you're using like at neutral solution or using like saturated gas, so it's better just to switch between like syringe pump or pressurized pump. It depends the application you are trying to use. So after that, we're talking about, okay, now we have the system, how we prepare our catalyst in the working electrode. So there's a lot of method to prepare your catalyst. The simplest one like is electrode deposition, where you can just insert our electrolyte. First, we flow the system with deionized water to be sure all the flow is working, everything is working well. After that, we replace the deionized water with our like our electrolyte, like in our case here, the copper sulfate. So if you need to use like deposit like copper or palladium or whatever the metal you are interested, you just bring your salt, dissolve it in the solution, and after that insert it in the syringe pump after, and waiting a little bit time, so that you can observe the open cycle potential will be starting to be stabilized. After that, after we see the open cycle potential stabilized, so now we are sure all the system will be full with our electrolyte in the copper sulfate solution. After that, we can simply use like cyclic voltammetry to observe the catalyst deposition and dissolution. As you can see here in this picture, when you go negative potential compared to positive potential, you can observe how the copper starting to grow in the platinum working electrode. And after we switch to the positive scan, so you can see how the copper is starting the dissolution in the electrolyte. So with this way, you can observe and control how much catalyst you need to deposit in your working electrode, and also you can control how like the mechanism, how it's cross mechanism. If you looking to studying the effect of the potential in different the gross formation, you can use this system very well. Other way you can use just apply chronoampermetry or potentiometry. So by controlling how much time you apply in constant potential, you can control how much deposit of the catalyst in the working electrode. Like for example, here it at 120 seconds. So you have the thickness of the catalyst in the working electrode is very small. By increasing the amount to 180 seconds, so you can see they have a lot of bunch of catalyst in the working electrode, and you can observe this very easy after that in the using the light microscope. So this one way to just deposit any catalyst in your working electrode, but not all the people they have prepared just electrode deposition. Some people using like sputtering or drop casting. So for this way, they have some limitation to use sputtering or drop casting, because if you drop casting or sputtering in the whole work in this chip is very small, so you get contaminate all the working electrode. It's localize your catalyst in the working electrode. But the prototype is provide like a very good technique, like it's called shadow mask. So you can cover the whole chip and just only expose the working electrode, so that you can easily deposit your catalyst directly in the working electrode by drop casting or use like sputtering. And also by controlling the concentration, you can control the thickness of this catalyst in the working electrode. So after that, but for the catalyst drop casting, they have some challenge you have to keep in mind. First, the particle size, because the spacer between the two silicon nitrile windows is around like 500 nanometer for the larger chip, and we can put another spacer in the small chip up to like 500, another 500. So the total space inside this system is around 1 micron. So if your particle size more than like 1 micron, like for example, this H-cast 3D structure is more than 2 micron. So for sure, whatever the catalyst you are deposit, after you try to close the system, the windows will be broken. So you have to be consider the particle size of your catalyst before you try to drop casting in your catalyst. But so for example, here the H-cast is like less than 200 nanometer. So that is good particle size. You can deposit the catalyst in the working electrode, and you don't have any the system. And the second challenging, you have to adjust the concentration of the ink. If you have much of the like high concentration ink, so you can get a lot of bunch of the particle size, a particle in the working electrode, localizing working electrode. In case if you have like very diluted ink, so we'll get like, the catalyst will deposit around the working electrode, but you don't have anything in the working electrode. So you have to be careful about what the concentration and for the ink when you starting to do drop casting in the working electrode. So after that, we prepare the catalyst, we do everything. After that, we need to how we could get acquisition and the data analysis for your system. So when you assemble this two silicon nitrile window under vacuum, you can see like when you insert the holder into the high vacuum in the TM, the liquid thickness was starting to blowing because the vacuum increased the thickness of the electrolyte. So that in the barrel configuration. But once you just change the configuration of this two silicon nitrile window from the bi configuration to cross configuration, you can adjust the liquid thickness, get it like very small, close to the edge. As you can see here, We compare here the barrel configuration and the cross configuration. Just simple measurement. We measure the intensity profile. As you can see here in the cross configuration setup, we can enhance the intensity of the the intensity profile by 3 times more than in the barrel configuration. So this gives you like high signal compared to the noise ratio in the inside when you're doing your experimental work. Also, during the electrochemical measurement, like you can introduce a lot of bubbles around the working electrode, but you can use these bubbles can be useful to displace this electrolyte towards the working electrode, and when you generate some bubbles between these two silicon nitrile window, you can reduce the liquid around the working electrode. After that, you can get high signal in the imaging compared to like if you have full of the electrolyte. But you have to be careful about like the bubbles. So by controlling the flow rate and the bubble formation around the working electrode, because if you get this electrode is completely dry, so your electrode will not be electrochemical active. So you have to be sure your working electrode is electrochemical active. So this one example, like here, once you in the first image here was before the bubble formation, and second one is after the bubble formation. As you can see here under the In-Situ TEM, how when the bubble formation started to generate, how the contrast of the working electrode enhance, and you can get very clear imaging at high resolution. But as I said before, we have to be sure the working electrode is still electrochemical active, still some electrolyte touch your working electrode. So you can do some measurement like yields measurement. So where you can try compare the dry cell with silicon nitrile window without any electrolyte with the liquid cell, and you can see here the plasmonic peak of the water is around the working electrodes. It gives you indication your working electrode is still electrochemical active. After that, after you control the liquid thickness by introducing the bubbles and control the configuration for using the cross configuration, so you can get very high signal like resolution imaging in the scanning EDX mapping. So in the first image, you can see the platinum and the copper sputtering we are using before. So here in the platinum connector, you can get like high signal for the platinum and the copper. And when you introduce the electrolyte, also you can even see how much the electrolyte distribute around the working electrode, and you can see the interface between the copper working electrode and the electrolyte, and you can see how much like have high signal for the oxygen due to you are introducing electrolyte around the working electrode. And by measurement, like here in the first image by the EDX, you can use the silicon to oxygen ratio to identify if your working electrode is still active or not. Like here in the first image, you can see from the platinum to copper in the dry cell, the silicon to oxygen peak is very small, like here, because you don't have any electrolyte. But once you introduce the electrolyte in the working electrode, here is just two area, you can see how much is like the oxygen to silicon area is starting to increase. This indicate your electrolyte touch your working electrode. And finally, what we get like ETM imaging, you get good imaging and to tracking the morphology and do EDX mapping. Also, you can do some selected area diffraction, and this can help you like not only just tracking the morphology and the particle size, but also you can track the phase structure under the liquid cell. This is very important application. So first we try like once we have very low thickness liquid under the TM, and we control the bubble, so you can get like this the platinum connector. You can get like the platinum signal for the diffraction, and you can analyze it these peaks compared to the theoretical. So you can see, you can identify all the lattice fringes, all the lattice phase and under the TM. After that, you can apply it in the any unknown catalyst, like for example, like copper or palladium, and you can identify once you apply different applied potential, you can get different phase structure between the copper to copper oxide or palladium to palladium hydride. And we use this one example, we used it before, like in our recent publication in Nature Communication. We use this technique to identify the changing of the palladium to palladium hydride under applied potential. So we can get like this the radial profile for the diffraction, and you can identify in different potential so you can identify the changing between palladium metallic phase to alpha and beta phase. And this is very important to get like indication, not only the morphology change, but also you can identify the phase structure as a function of applied potential. And final thing, for the dose rate and accumulated dose, it's important to optimizing the dose rate, because once you see any change, you have to be sure this is a change coming from the electrochemical behavior, not due to the dose you apply in the system. As you can see, once you increase the dose rate, you can see the dose can enough to get the particle started to grow. So this growth coming from like the dose rate, not from the electrochemical, when not due to like applied potential or any external measurement. And by multiply this dose rate, also not only you can introduce the particle growth in very short time, but also you can introduce dissolution at very high dose rate, accumulated dose rate. So it is important to determine the threshold, what the dose rate you can use during the measurement when you apply any electrochemical measurement, to be sure this behavior or this change happening due to your application, not due to the effect of the dose rate and the accumulated dose. So to summary what we're talking about. So we're talking about like how the pressurized pump can enhance the electrochemical processing by maintaining the saturated gas environment for certain reaction. We can optimizing the technique for the catalyst layer preparation by using electrodeposition, sputtering, or drop casting. And also it's important to managing the liquid thickness and also the gas bubble formation, so we can control the thickness of the electrolyte and enhance the signal for the analysis. But be sure to ensure like you have ionic conductivity between the electrode. And also we show like how the selected area diffraction can be powerful technique to studying the phase structure under the electrochemical processing. And finally we need to be ensure to establish the electron dose threshold to be sure we don't have any beam effect and during your experimental, by using like Faraday cap or using the Axiom dose software that provides from the prototype. And finally, if you need to read more about our technique paper, like in small method, this is the paper. And also if you need to read more about like how we use the selected area diffraction to identify the transformation between the palladium to palladium hydride and the carbon dioxide reduction, for our paper in Nature Communication. This is our paper. I put the link here. And if you have any question, please let me know and be in touch. I will happy to help. And finally, I want to acknowledge all my previous group, like Higgins group and Drew Higgins, Khulud, Lisa, Dr. Catherine, Fatma, and Amir, and all the foundations they funded this project. And thank you for your attention.